Okay, so in this little video here, what I'm going to do is do a quick overview of orbitals, and then we're going to go from that into electron configurations. So when n is equal to 1, we can have values of L that are as high as 0. That's n minus 1. And when n is equal to 2, L can have values of 0 or 1. When it's 3, 0, 1, or 2. And when it's 4, 0, 1, 2, or 3. And because of what m sub L is, sort of telling us the orientations of these orbitals, we can get to the number of electrons that are allowed in each. So the kinds of orbitals that are available in the first energy level are just s. When L is equal to 0 or 1, it can be s or p. When it's 0, 1, or 2, s, p, or d. And when it's 0, 1, 2, or 3, s, p, d, and f. And we should probably remember that there is one kind of s orbital. So there's only one kind of s. There's 3 kinds of p. There's 5 kinds of d, and there's 7 kinds of f. Okay? So the total number of orbitals at the s at the first energy level is just 1. The total number of orbitals is 1 from the s and 3 from the p, which is 4. The total number from the third energy level is 1 from the s, 3 from the p's, 5 from the d's, and that brings us to 9. And 1 plus 3 plus 5 plus 7 brings us to 16. Basically, it's whatever n is squared. The total number of orbitals, knowing that every orbital can fit 2 electrons, is double this number. So 2 electrons in the first energy level, 8 in the second, 18 in the third, 32 here, so this is basically 2n squared. And it's important for us to remember that orbitals are volumes of space where an electron can be found. So remember, this is a probability. Okay? It's not a certainty. It's not an orbit. Okay? And our goal is to account for all electrons in an atom or an ion. So now we're going to work on electron configuration for these atoms. So these are the ones we're listing here. We're going to stick to the first and second energy level with sort of a brief introduction to the third. So if I'm talking about an atom with just 1 electron, just 1 proton, we're talking about hydrogen. So there is 1 electron here, and I'm going to show that this is our way of showing a single electron, like that. So there's a single electron right there. So I could say that hydrogen has 1 electron as a superscript in the s-shaped orbital, lowercase letter, of the first energy level. So 1s1 would be its electron configuration. Helium has 1 more electron. So it goes here. Each orbital can hold up to 2 electrons. And I'm going to show it in the opposite direction because it's got an opposite spin. And I can say that there are 2 electrons as a superscript in the s-shaped orbital of the first energy level. So 1s2 is helium's electron configuration. Now I'm out of room in the 1s orbital, so now I need to move up an energy level, and I'm in the 2s's now. So if I'm talking about lithium, there's another electron there. There are 3 electrons in lithium. So there is 1 electron in the s-shaped orbital of the second energy level, 2 electrons in the s-shaped orbital of the first energy level. And so you can start to see a pattern starting to arise. So if I'm talking about boron, boron is the 5th element, so there should be 5 electrons. So there's another electron that must be here. And then the others, there's no more room in the s's, so we must go into the p's. So these are the 2 p's. So boron would have an electron here. And it would be, there'd be 1 electron in the p-shaped orbital of the second energy level, 2 electrons in the s-shaped orbital of the second energy level, and 2 electrons in the s-shaped orbital of the first energy level. So 1s2, 2s2, 2p1. Carbon would be next. Now the next electron for carbon does not buddy up here. Electrons would like to spread out. This is called Hund's rule, or often known as the bus rule. And so that next electron goes here. It does not change what electron configuration of it is. And I'm going to start writing these left to right like I normally would. So 1s2, 2s2, 2p2. I've got 2 here, and 2 here. That's what these 2's mean. Oxygen is next, and so that would be, let's see, I've got 2 more electrons that go into oxygen. So it would look like this. So 1s2, 2s2, 2p, 1, 2, 3, 4. Fluorine would be like this. So 1s2, 2s2, 2p, 5. Now I'm going to do fluoride. And the important thing about fluoride is I've got this negative charge here. That means it's got 1 extra electron. Well, I've got space for 1 extra electron. And it would go right there. So 1s2, 2s2, 2p6. Okay? So for an anion, we add 1 electron. And then neon has the same number of electrons. It's got 2, 4, 6, 8, 10 electrons. It's the 10th element if it's neutral. So 1s2, 2s2, 2p6. These 2 are not the same element, but they have the same number of electrons, and they're referred to as isoelectronic. And another very important thing to remember is that the sum of the superscripts, so these numbers here, so I'll call them supers, is equal to the number of electrons that the atom should have, either the ion or the element. Okay, so the next video we'll pick up at the 3rd energy level here and see where that takes us, because we're out of space here. So the next ones would be the 3 S's, and there's some neat things that happen with the 3rd energy level, and we get to learn a little shortcut too.